master equation for spin dynamics. So this is the equation which underpins actually most of the theory that at least I've done in NMR for a long time, and in fact most of the NMR world. And the simulation methods that we use as well employ essentially a master equation for predicting how nuclear spins behave. And the same applies actually for electron spins, although that's a field I know less about. Right, can I just move this stuff out of the way? Yeah, all right. Right, so we first of all distinguish between what's called a closed quantum system, which is, so the, well, our spin system in NMR is an example of a quantum system. And we can view it in the terms as a closed quantum system, one which doesn't interact with its environment, at least locally for some time, or an open system which does interact with its environment. For a closed system, the master equation we use is this thing called the Levitt-von Neumann equation. The state of the spin system is described by a density operator, and we have a Hamiltonian which derives. And we tend to super operator sort of notation for this these days. Yeah, in which that's represented by a commutation super operator with a hat, just so that those of you following this can understand what I mean there. So single hats mean commutation super operators. Right, so that's the Levitt-von Neumann equation, and it's very well known and well established. When we have an open quantum system, so where the quantum system's interacting with the bath, so this could be a nuclear spin system interacting with the molecular environment, then we have to model that system bath interaction, and that's done by introducing something called a relaxation superoperator. And there's a very well established theory in NMR and other fields of physics about how to do that under certain assumptions. There's ways of calculating the relaxation superoperator. One has to be aware of the various approximations which you use when constructing that. And there's a very thorny problem really in how you take into account the fact that the bath, the molecular environment, has a finite temperature. And actually this particular problem is one which, to some extent, I think everyone in NMR who's tried to indulge in real theory sort of breaks their head upon at some point. It's terribly difficult and a dangerous piece of theory. And we'll see, actually, I'm going to argue that this, in fact, defeated really all of the people we now know as the giants of the field in NMR. To do this in a general way, at least. So what we do in our field is we use something called the semi-classical relaxation superoperator. And the names associated with this are all the famous names in NMR in the 1950s and 1960s, Bloch, Bloombergen, Abraham, Redfield, and so on. And these guys, to develop this theory, it was a tremendous achievement. They assumed that the spin-bath interactions are fluctuating. That could be, for example, a dipole-dipole coupling, which causes relaxation in solution. They also had to assume, actually, that the temperature of the bath was infinite, at least temporarily. We'll come back to that in a minute. And you come up with a form for the relaxation superoperator, which looks something like this. This is an example for dipole-dipole relaxation in a liquid. We're not going to go into details, but I just want to show what it looks like. You have various spherical tensor operators. These are commutation superoperators of those, and you have spectral density functions. And there are relaxation superoperators for every conceivable relaxation mechanism, and you can look them up in various textbooks and so on, and they all look more or less something similar to this. And then, for example, programs like Spin Dynamica, our simulation, and algebraic system for understanding relaxation, studying long-lived states and other things. This is the sort of thing we use. You can program this type of thing straight into Spin Dynamica. And of course, it works superbly well, except that it assumes an infinite bath temperature. Just to give you an example of what these things look like, without going into details here, I don't want to spend too much time on it, but you can write this superoperator as a matrix in something called Liouville space. And it has this block structure. These are coherence orders. So the thing in the middle here is a zero quantum block, and then you get different blocks for the different orders of coherence. And this is sort of well known in the field as something called the Redfield kite. So where you have the head of the kite and then a tail with smaller blocks attached to it. So that's all standard theory, and a great deal of NMR development has been based on this type of thing. If we look at a few particular elements in this matrix, like this one down here, is actually in solution NMR would be called W2, and it's the transition probability for spins to go from the alpha alpha to the beta state, a double quantum transition. You can see it's larger than the other ones. This is dipole-dipole relaxation in the liquid. Double quantum transitions dominate, and you also have an element for the transition in the opposite sense. And as you see from the coloring here, the two transitions are equal. Two transition probabilities are equal. And that's a characteristic of an infinite temperature. So we have a sort of problem that the relaxation theory, the semi-classical relaxation theory, inevitably leads to equal transition probabilities going up and down. And that means that in equilibrium, after you leave the system for a long time, the spin order vanishes. So we get no thermal magnetization, nothing at all. And of course, that's not physically correct. And in fact, the entire, of course, NMR depends on having thermal polarization of some kind, or for electrons, the same. So this is clearly a problem, and the early workers in the field grappled with it. And essentially, there are now two ways of handling this. So the NMR world chose one route, which was to keep the relaxation superoperator the same, but use a different equation, which had been fiddled with in order to give the right thermal equilibrium. And that's the approach chosen by Abraham, Redfield, and the other workers in the field. Now, at the same time as NMR was developing this stuff, then there was a developing field of essentially mathematical quantum physics, which interacted more closely with other fields like the developing science of optics. For example, the laser was developed at roughly the same time as these guys who were working in NMR, on the NMR theory. And they chose a different route, which is to keep the master equation as it is, but use a different form for the relaxation superoperator. And in particular, take into account the temperature of the bath. And in fact, there were lots of people working in this area, but the two names who receive prominence now are called Kosakowski and Lindblad. And they published a series of papers between the 70s and 80s, which essentially laid out how to do this. So this theory was not available to Abraham and Redfield. So it's understandable that they chose essentially a fudged equation rather than trying to do it properly. In fact, if you read Abraham's book, most of it is, of course, is absolutely wonderful, but there are some extraordinarily weak sections on this particular problem. One of which, I mean, readings again, I was sort of shocked actually. It's clearly that both of these guys, they knew which equation they wanted to get to, and then sweated and cursed as they tried to justify it, and basically failed. And there's a particular couple of pages in Abraham which just completely runs into the sand and gets nowhere. And then clearly he then moves on to something else. And the reason is that they didn't have this theory available. So in the NMR world, through various approximations, which are very strong approximations actually, stating that the spin system is always close to equilibrium and there's always a small amount of spin order, you could hack your way through to this equation, which is what they wanted to get to, and that's called the inhomogeneous master equation, it has this rather ugly form where the thermal equilibrium density operator only appears in one term. And this is basically this fudge, which was just introduced by these guys to make sure they got the right thermal equilibrium value out of the equation. And it was poorly justified, you have to admit, in general, although they were fully aware that by deriving this equation, they were making some big assumptions. And in fact, in one place, Redfield uses this rather nice wording here. In moving from one set of equations to the next, it has to make the statement, unless the system is prepared in some unusual way. And I'll get back to what that means. Now, the mathematical physicists developing open quantum systems theory, they went a different way. So they used the same equation, same master equation, but with a relaxation superoperator. Here I'm just using the theta to mean thermalization. That this has now been adjusted for the temperature of the environment. And then to form that, the relaxation superoperator is changed. And instead of the commutation superoperators, one uses a pretty nasty sounding thing called a Lindbladian or Lindbladian dissipator. Plus one introduces some thermal terms. You see the temperature appearing here in the spectral densities. And this is the key to the whole thing, is this particular superoperator, which was developed by Kosakowski and Lindblad. In fact, if you look on Wikipedia and look at Lindbladian in Wikipedia, there's a very informative page, which actually I only came across, Christian showed this to me yesterday, actually. It seems that this equation is now more frequently known as the GKSL equation, which stands for these four guys. Sudarshan actually was a very famous physicist indeed, who most people feel should have got the Nobel Prize for work which was essentially copied by Glauber, who got the Nobel Prize instead. But anyway, these guys developed this particular form of a superoperator. It's a strange thing, but no matter, spin dynamica can handle it. This is the superoperator matrix representation for this Lindbladian-based relaxation superoperator. And at high temperature, so where the temperature is much larger than the Larmor frequency in our terms, 100 times larger, it looks the same. But as we go down in the spin temperature to 5 times the Larmor frequency, and then 1 times the Larmor frequency, we see that this imbalance appears, where the transition probability going down in energy becomes much larger than the transition probability going up in energy. There are subtle changes to the coherence decays as well. And as we go to very low spin temperature, so if this was just thermal spin temperature, we'd be down here in the micro-Kelvin regime in NMR, and you get a strong imbalance between the two transition probabilities. But this Lindbladian approach predicts the correct thermal equilibrium for the density operator, and also fulfills many different mathematical properties which are essential for a valid master equation, which I won't go into. So this is the proper way of doing it. And in fact, if you program that in with spin dynamica, as we've done, and do some standard solution state relaxation experiments, such as the nuclear Overhauser effect, you predict all the same things that the ordinary master equation predicts as well. So there's no difference for ordinary NMR on ordinarily weakly polarized spin systems at high temperature. So here, for example, this is tracking the magnetization of 2 different spin isotope types, one of which you apply an RF field to, so it executes these oscillations. The other one then picks up magnetization through the steady state nuclear Overhauser effect. So all of these well-known effects to do with thermal polarization in standard NMR. Now, the interesting thing happens is when you start to consider systems which are prepared in an unusual way, in the phrase of Redfield. And remember that Redfield said that if the system is prepared in an unusual way, then that particular derivation of the master equation we breaks down. It's not valid. And he was completely right in that. So what is a system prepared in an unusual way? It means with large amounts of spin order, it could be far from equilibrium. And typical examples should be strong hyperpolarization, if you have different populations of spin isomers, well displaced from equilibrium, or even equilibrium systems at very low temperature. And of course, all of those things are nowadays at the very forefront of what we're doing in NMR. Hyperpolarization, parahydrogen, quantum rotors, they're all in this category. So you have to wonder, does the master equation actually work? And the answer is, in general, it doesn't. Although usually it does. So here's an example. And it comes from our work on long-lived singlet states in solution NMR. So suppose we have pairs of spins a half, and suppose they're magnetically equivalent. So this could be water, for example. Protons, magnetically equivalent. And we have a singlet state with total spin 0, and we have 3 triplet states with total spin 1. Let's look at the relaxation dynamics in this system. So if you put water in an NMR tube and put it in the magnet, then magnetization builds up. That's the T1 process. And that's associated with transitions from the upper triplet state to the lower triplet state. And the process is relatively fast, so T1 is short. So let's say that T1 is, say, a second or 2 seconds. Magnetization builds up with T1, and that's associated with this transition probability from the upper triplet state to the lower triplet state. In general, you can do other things with this spin system. So you could imagine putting a population in the singlet state. We'll see in a minute how that can actually be done experimentally. So you now have an imbalance of populations between singlets and so the singlet state is enhanced, the triplet state is depleted. And that will also relax back to equilibrium, but it does so very slowly in general. So we call that time constant Ts for the decay of singlet order. And it's a much slower process usually. Okay, so that's the sort of background. Now, suppose we prepare the system in an unusual way. So let's say, for the sake of simplicity, that the system is prepared somehow in a pure singlet state. So all of the water molecules are in the singlet state. The total magnetization in this state is 0. Magnetization is associated with triplet state, and there isn't any population in the triplet state. And now we ask the question, how does the magnetization build up now? Does it build up with Ts or with T1? And in an ideal world, I'll give you a few moments to think about that and guess what the answer is. It turns out that these two approaches to relaxation theory give different answers here. So the ordinary master equation, which we always use, predicts that it builds up with T1. So a second or so. The Lindbladian equation predicts that it builds up with Ts, completely different physical prediction. A much slower buildup. So in principle, one could test that. And in fact, we had done an experiment a couple of years ago, a few years ago now, which did test that, did actually measure that. What we did is a bit obscure. We have a long-standing collaboration in which we study the spectroscopy, not just NMR, but other things as well, of molecules trapped inside fullerene cages. So this is water in C60. So we have a freely rotating water molecule which actually behaves according to the laws of quantum mechanics, even at very low temperature. It's freely rotating. It has a set of energy levels which are similar to water in the gas phase. I won't go into details, but it has 3 quantum numbers actually for the rotational levels. But you have para water and you have ortho water. And in particular, the para water is about 30 Kelvin lower in energy than the ortho water. So if you cool this stuff with liquid helium and wait, you can generate pure para water inside the cage. And that's in the pure nuclear singlet state. So then what you can do is you can have the sample in a cold cryostat in liquid helium for a long time, and then fire it as a bullet, and then dissolve it in a solvent in the NMR magnet. And that's a piece of apparatus which Benno Meyer and Karol Kaujal and Hanna Kaujilova did in our lab a few years ago. In fact, this particular piece of apparatus was later adapted to do DNP as well. And that's something that Benno is working on. But here I just want to talk about this particular experiment. So the sample is then enriched, is para water, enriched with para water and then dissolved. And then you just watch the NMR signal. And it grows because the para water converts to ortho water. And that's the TS process, and it's slow. It grows in with about 30 seconds, and that's much longer than T1. So basically, Lindblad wins. The Lindblad theory is the correct description of this relaxation. And in fact, if you think about it a bit, actually, you can realize that the predictions of the ordinary master equation we use is just completely crazy. It would be predicting that magnetization builds up in a system which doesn't have any nuclear spin, which doesn't make any physical sense at all. So very clearly, the Lindbladian theory is the correct way of doing this. So just to summarize, the inhomogeneous master equation has been with us for more than 50 years, but it's probably now past its shelf life. As soon as we go into systems which are far from equilibrium, as many of us work with now, then you have to at least hold in some doubt as to whether the equation is correct. And these limitations were well known to the developers in the 60s, but I would say, at least in my judgment, most of us have forgotten about that. And it's been used just blindly, actually, ever since, sometimes in situations where it's not correct. Meanwhile, the mathematical physics community and also the people working with coherent optics and later on quantum information, they use a different master equation. But the NMR community has been isolated from that community to a large extent, although that's just starting to break down, that isolation bit. And so they developed a different way and a more rigorous way of doing it. As an aside, actually, myself with Lorenzo Di Bari and earlier Genier had experimented with different forms of the master equation. And in fact, these do remedy some of the defects of the master equation, but not all of them. So I wouldn't recommend going that way anymore. Yeah, so now we run into limitations of the inhomogeneous master equation. And that hasn't escaped the attention of the entire NMR community. So there may be more, but we're aware of 2 papers at least, both of them are rather recent. So Alexander Karabanov is a really serious mathematical physicist, and in developing his DNP theory together with Walter Kuchenberger, it was a matter of course for him to use the Lindbladian. He wouldn't have dreamt of using the inhomogeneous master equation. So his papers actually do use the Lindbladian. And also David Corey and his group, who are also very much involved in quantum information theory, which uses Lindbladians, they use that to describe NMR as well. So this is not entirely or by any means original. Nevertheless, I think that Christian here has provided a very clear and solid formulation of the Lindbladian master equation for NMR. which has been incorporated into Spin Dynamica and which gives us a solid basis on which to perform our theory and simulations in the future. And with that, I thank especially Christian, the group of Richard Whitby, who synthesized the endofullerenes, and Ben O'Meyer and Carol and Hannah for some years ago now performing those experiments on the water endofullerene. So thank you very much, and I'll be very happy to answer questions.
All right, thank you very much, Malcolm, for your very nice reformulation of the master equations. I mean, so a couple of years ago when I was trying to write my DMP code, actually I stumbled upon these questions in homogeneous master equation. It was actually very difficult, and then that's the part that I spent the most time. And then I came across your paper with DiBari, 1992, and also Levitt and us. Levitt and Richard us, they have the thermal correction. So actually, I did use the fudge equation to fudge my to introduce the rho EQ because there wasn't a better way.
Yeah,
and
I mean, basically, we just used we introduced a different style of fudge, basically.
Exactly. And then I read Walter Kochenberger paper in PRL, and then Lindbladian, and it was like, wow, there's a lot of stuff, and I would go back to it if I have time. But maybe I'll just start with a simple question so that people have time to type and vote on your questions. So actually, I don't have time to go through the paper. Yes, about 200 equations. So I'm just curious for your new generalized master equations. I read it through briefly, and then one of the criteria is that you need to have a coherent a Hamiltonian that's secular, that's much bigger than other terms. So I was just wondering, so if I were to treat a Hamiltonian that has the bigger part, the Zeeman and the dipolar order, they are not several order of magnitude difference. I mean, I'm just wondering is there a case where the perturbation approach that you use is not valid anymore? For example, you have the hyperfine coupling that's very close, where it's very similar in magnitude compared to your Zeeman, where the perturbation is not very good. Is there a way that you can diagonalize the entire Hamiltonian and find a new set of autonomous eigenbases and apply this? I might be,
yes,
I might sound boost. Yeah.
Yeah, no, I understand. Yeah, it's true that in our paper, actually, then we concentrated mainly because on problems in solution NMR, where usually there's a single very dominant Hamiltonian. But as you say, then, yeah, there is a more general cases where you have a more general coherent Hamiltonian, which could involve all sorts of competing large terms, like you often have in solution NMR. And yeah, well, at least in principle, if you have a small spin system as an approximation to start with, you can diagonalize it. There is still an approximation, though. You have to be, I think, there's still an approximation that one has to be careful with, which is that you have some interaction which is fluctuating and causing the relaxation. And that interaction still has to be small compared to eigenvalue spacings. So yeah, I think, I mean, all relaxation theories involve approximations. There's also whether the size of the fluctuating Hamiltonian is small compared to its correlation time. I think one has to look at each of these approximations very carefully in systems like that. There will be situations in which, there's no available master equation. And actually, there's a whole field of open quantum systems theory, which is incredibly sophisticated and on a very high level, and trying to attack the most general types of problems involving spin-Bath or system-Bath interactions. So it's very hard to give a very clear general answer to that, actually.
Okay, thank you. Because this is actually one of the conversations that I have with Kochenberger 6 years ago in India, in a conference. And then because Kochenberger was trying to model the spin diffusion, from the closely space from the nuclide that's very close to the electron to the bulk. And how do we do this? Because like the nuclide that's close to the electron, it has a strong hyperfine, and the basis is not really in the Zeeman on, it's in the tilted axis. And how the species got out from it, this is disputable. And then do we need to find a new basis for this special kind of nucleus? So this is something that we had, and then like we were wondering how to do this. Yeah.
I mean, I think in general, what we really need is for the NMR world to get out of its shell, in which we've buried ourselves for 50 years, and start talking to serious mathematical physicists who are working on very similar problems. And I think it's now really time for us to do that and recognize that our field is only a subfield of a much larger area of physics.
Exactly.
In which extremely clever people are working away.
I fully agree with you. I think there's definitely a lot of things to do for the theorists in NMR to approach the physicists, rather than like reinventing the views ourselves. So I think I will now address the questions because we have 14 questions to line up. So first question from Jeffrey, Jeff Reimer, are you going to change the approach to relaxation in your textbook?
Well, I think Jeff, yeah, I think I would at least mention, if I did, which I'm not, by the way, going to write a new edition or something, I probably would try to use the Lindbladian approach from the beginning. Maybe I would have to think about it, but yeah, I would consider it at least.
Okay, next question from John. Does the Lindblad formulation also allow you to deal with things like spin projection noise?
Oh God, I don't know, John. I don't even know what that is. I suspect you know the answer, but to that better than I do.
John, would you like to comment? Yeah, I see. Allowed to talk. You can unmute yourself and talk now. John?
Am I unmuted?
Yes, you are. We can hear you.
Yeah, I can hear you.
Okay. And so this is on my mind because, you know, crazy things where we do talk to the physicists sometimes. So if you think about when you have a single spin, it has this random chance of being projected in any different direction. And in fact, even if you look at the original paper by Bloch, he points out that even if you have your spins all magnetized along one axis, still square root n of them should be projected onto the transverse plane.
Right, so there's noise, basically, right?
Yeah, by Norbert Müller,
Yep.
He did something on that, and I think Richard Ernst also did something early in his beginning time, if I'm not mistaken.
Yeah, and Irwin and Pico Slater. There's a little bit of subtle difference between the fundamental version and the version where it's coupled to your pickup circuit.
Yeah.
But I wonder if some of these quantum effects that are important, for example, in single spin NMR, like detected with NVs, if that can also be readily treated by this sort of system, the Lindblad.
I believe so. I think that's the way to go. I think actually if Christian's online, then I think he can say more about this.
Yep.
But the open quantum system, the theory people, you know, they deal a lot also with the problem of observation and
Yep.
you know, there's these Lindbladians all over the place. So I think that's the right way of doing that.
Christian, you are actually allowed to talk now. So
Cool.
would you like to comment, Christian? You can unmute yourself.
Yep. Hey. To be fair, I already thought about the same experiment, and it's good to see that others, Bloch already. And if you have a single spin, you could ask yourself, on average, for example. So usually in NMR we work with ensembles, but and then we make the ergodic approximation, for example. But you have a single spin, and you could also ask yourself if it will in time reproduce the Boltzmann distribution, for example. And I think this is basically what you mean in some sense. And from a mathematical point of view, I would say it should be encaptured by the Lindblad form because, let's say, from a theoretical point of view, any Markovian process has to admit some Lindblad form. This is more like a mathematical theorem, so to speak. The question is, what does that Lindblad form look like? And I don't know. Yeah,
That's a good point.
I guess that's the, you know, the relaxation constants could be time dependent or something like that. It doesn't mean in NMR, the relaxation constants are usually time independent, or we assume that. But it could be that not only that the relaxation constants are changing in time, but also the eigenbasis is changing in time, which could still at each point in time constitute a Lindblad form, but it might not be as simple as we are used to from our usual master equations.
Okay, thank you. So I'll just move on to the next question from Alex. So you mentioned that, so for your new master equation, it is almost always better than the inhomogeneous master equation. And does it produce any insight? And can you comment on the computational efficiency, Malcolm?
Well, yeah, to say the last point first, it's not something that we've really assessed, but I don't see an obvious reason why it would be less computationally efficient than the master equation. Actually, in spin dynamica, we anyway use our sort of fudge, the one I did with Lorenzo Di Bari many years ago, rather than the inhomogeneous master equation. Well, I don't know in detail, but I don't believe it has substantial computational loss of computational efficiency. I don't think so. And physical insight, well, to me, it gives more actually. It relates much more easily into the transition probabilities. You can see the transition probabilities going up and down the different. And it's obvious that that leads to the, well, it fulfills detailed balance. It links better in if you're combining NMR spin dynamics with, say, chemical dynamics, where again you have detailed balance between the reacting species. It's actually more intuitive, in my opinion, than the inhomogeneous master equation. I think once you start working with it, you realize that the inhomogeneous master equation is just, it's just horrible. It's just an ugly thing. But that's a personal view.
Okay, thank you. So next question from Jeffrey. Does your thermal correction factor you developed with Lorenzo Di Bari still hold in your 1992 PRL paper?
Yeah, so this was a different way of fudging. So this converted the inhomogeneous master equation into a homogeneous master equation and with a thermalized relaxation superoperator. So in that respect, it's just the same as it's the same philosophy as doing the Lindbladian approach. It's just that our form of the thermalized relaxation superoperator, and actually also the ones proposed by Jean Genet and Levitt and Ernst, they're not rigorous. So they don't satisfy the rigorous physical conditions of open quantum systems theory. So they're not actually really grounded in proper physics. So I would say that this Lindbladian form supersedes those papers.
Okay, next question from Olivia. Could this master equation be useful to model Maser effects in hyperpolarized samples?
Right, yeah, so, well, yes, I'm sure it can, yeah. And I think, given the fact that the theory of lasers, I think also uses a very, and spontaneous emission and so on, uses Lindbladians, then I'm pretty confident that the theory of masers, or rasers for that matter, could and probably should be formulated the same way as well.
Okay. Next question from Chris. What is the prediction of Lindbladian when after DMP enhancement and wait for relaxation? Will it follow T1?
Yes, I think so. So I got to, I mean, I have to say this, that there's a question which hasn't been asked yet, but which I would have probably asked if I'd listened to this talk, which is sort of like, how do I know when I need to use this Lindbladian form and not the ordinary master equation? And my answer to that, which is related to the answer to this one, is probably that in 99% of experiments, it won't make any difference. but there might, there are some rare cases where it does make a difference. One of them I just highlighted. And since it's the correct form, then why not just do it? Actually, I've lost the original question now. What was it?
It's okay. It was probably dismissed somewhere. Would you mind if I just keep on asking the next question from Jeffrey?
Yeah.
All right. So Jeffrey asked, like, in his mind, no doubt distorted by Redfield, it seems obvious that 1 over TS acts like a bottleneck, i.e. a rate limiting step in the transfer from a pure single state to a triple manifold. I do not wish to challenge the Lindbladian, but your example does not appear to provide a compelling reason to use it.
Well, I would argue that it does actually, Jeffrey, because your insight, of course, is completely right. That's exactly what happened. The only problem is that's not what the inhomogeneous master equation says. It doesn't predict that very obvious physical explanation that you give. It doesn't, but the Lindbladian formulation does. So that is should be your compelling reason to use it.
Jeffrey, I actually allowed you to talk. So, like, if you want to.
Well, apparently my intuition is better than Redfield. Maybe not as good as Lindblad.
Yeah, I mean, intuitively, it's absolutely right. TS is the bottleneck, so it has to come back with TS, for sure. It's just the baffling thing is that if you put in that the situation into the inhomogeneous master equation, as we did, and then ask it to, it simply gives you back the answer that it comes back with T1, which is clearly completely physically impossible. So then you immediately know, once you've satisfied that you haven't made some stupid mistake, you then immediately know the inhomogeneous master equation is deeply wrong in this situation.
All right. Okay. So, like, I will move on.
Can I maybe add one thing to that real quick?
Perfect. Yeah, sure.
So maybe to add to the intuition that's going on, it's not just that the Lindblad form itself provides a fixing of the rates, but if you look at it more closely, because of the different super operator that is being used, rather than so usually we use double commutators, and now we went on to using these Lindbladian dissipators. They provide a different mathematical structure. So let's say if you express that in some operator basis, the matrix representation looks different. It provides a different system of equations. So the dynamics that are predicted are different. There are new elements popping up in the Lindblad formulation that you don't have in the IME. And that is the key actually to why, the Lindblad formulation provides a correct description of the singlet decay in comparison to the IME.
Okay, so we actually have a lot of questions, and I will just probably just go through the list and pick like several questions. So Ilya asked, like, the steady state was easy with inhomogeneous master equation, just a matrix inverse. Now we have some strange null space. Any insights, Malcolm?
Well, okay, it's a good question, but I think the steady state becomes really easy actually in this formulation. In the IME is, I don't know, it's maybe obviously you have something in mind there, but you don't have, since the equation is inhomogeneous, you don't have a single generator which you can take the null space of to derive the steady state. So you have to homogenize the equation. That's what I tried to do with that work back in the 1980s in order to use the null space to get the steady state. In fact, that was precisely what that paper was on. Yeah.
What I mean is when you do, for example, DNP steady state under microwave irradiation, there's a very quick way of computing it. You say at the steady state, the time derivative is 0. You zero the time derivative, and then in the inhomogeneous equation, the R times rho equilibrium is a wonderful right-hand side, right? So you have a vector, then the inverse of an operator, and that's your steady state density matrix. In the Lindblad formalism, you don't have this little term. If you put the time derivative to 0, the equation that you now have is some super operator times rho equals 0.
Right.
Which no longer has a single solution.
Well, the way it does is you have a null space, right, for the.
That's right.
But then you have an additional constraint that the trace has to be 1.
So you think that,
operator,
that helps?
Yeah, so the only solution is the thermal equilibrium state, I think.
Okay.
Yeah, I mean, there's a different way of getting to the same thing, but I don't think it's more difficult.
Okay, so I have a similar question from Palmer. So does the theory say anything about the equilibrium density operator as the trace of the exponential of the Hamiltonian? There seems to be some controversy in physics over how one justified the statement.
Oh, that's a really interesting question, Art. I think I'm going to have to ask you the question otherwise. I mean, is it about, I mean, is your question, Art, about whether the Boltzmann distribution actually applies in detail?
So after you're allowed to talk now, yeah.
Right, so, I mean, we all start by writing down that the equilibrium density operator is this trace operation and say this must be right because it gives back the Boltzmann equilibrium populations that we expect. But there seems, in my limited reading in the physics literature, some debate over how you would rigorously justify that was the right thing to do. Even though, and in Jeffrey's words, it seems obvious.
Yeah, well, I mean, these are really deep questions. I don't know. I think it's not, you know, it's sort of obvious, but it's one of those obvious things that you have to think about for, 10 days and then decide, yes, it is obvious, which maybe is a strange definition of obvious. I don't know. So in, nuclear spin systems, we have systems of identical particles, which are not supposed to follow the Boltzmann distribution, right? They're supposed to follow the, Fermi-Dirac distribution or the Bose-Einstein distribution. So it's not at least obvious to me how the Boltzmann distribution actually emerges from that. But beyond that, I really don't know how that all works. So well, yeah, it's a very deep question you asked there, and I think it's not something we could, I can't answer it.
Okay, we have, I'll probably just take the last question. So I will, Chen, would you like to ask? So Chen is our former postdoc, and we are actually writing a paper on a DMP simulation.
Okay.
Chen?
Right, so I basically have similar questions before about thermal equilibrium. So basically, when we actually use the equation to apply it, and then we need to consider boundary conditions, right? And then I think those are important that those has direct physical meanings to me. So I find that although the inhomogeneous master equation looks ugly, but as already asked before, at thermal equilibrium, naturally from the d rho divided by dt equals to 0, and then we nicely have a thermal equilibrium, and then thus also match the physical intuition. So would you like to comment more about that, about the physical intuition of the equation? Because according to me, all equation at some point make some approximation and has some level of approximation. All theories are, after all, wrong, but some are more useful. That's what I heard. But would you mind comment more on the physical intuition at thermal equilibrium?
Yeah, I mean, I guess the first thing to answer in if you're contemplating which equation you should use for a certain problem is it safe to use? I mean, so if you're dealing with some hyperpolarized spin system or parahydrogen or something, chemically induced dynamic nuclear polarization, something like that, then you know immediately that you're preparing a system in an unusual way. So you're not fulfilling the approximations laid out by Redfield and Abraham. So then you have to worry immediately, is that equation actually, in principle, the derivation of that equation is breaks down. So you can't rely on it as being valid. And then, you know, you might find it physically intuitive, but if it's wrong, it's still not going to be any good for you, right? Now, as I said, though, in the vast majority of cases, it probably doesn't matter. Nevertheless, I would sort of say it's probably best just to use something which is mathematically correct.
Right. So then, so my follow-up
then
question.
I do find that it's physically intuitive as well, but that becomes a matter of personal taste. It just, once you work with these things, then you start to find them more intuitive and obvious.
Right. Yeah. So yeah, thanks for the explanation. Then, like, what is the biggest strength in comparison with the inhomogeneous master equation in terms of the accuracy it provides? Like, would there be a like example or something?
Well, I think this example I gave, which we hit upon, is a very good one because it just displays a very large qualitative difference between these two equations.
Yeah, that's true. Okay.
Now that, you know, in many cases, it won't be like that, that maybe there's just a small difference or no discernible difference at all. But, you know, given a choice then between one equation, which you know relies on assumptions which are not valid for the system that you're dealing with, and another one which is valid, but still has its approximations in it, then you would at least choose the one which is valid, surely.
All right. Okay.
Maybe
okay,
can I maybe add one more thing, because this question of stationary distribution has come up quite a lot in the last couple of questions, and so there's no doubt. So maybe in regards to Ilya's question, for example, the stationary state will always be the Boltzmann state of the coherent Hamiltonian that you use for example, as the main Hamiltonian. So in this case, for example, the Zeeman distribution. And that is forced because of the way, so the Lindblad dissipator obeys the detailed balance condition. And that will be according to the populations of, let's say, the Zeeman Hamiltonian in this case. And then because the Lindbladian describes a Markovian process from Markov theory, it's quite clear that the stationary, if you have a Markov process which obeys detailed balance, that the stationary distribution will be given by the corresponding by, let's say, that Boltzmann state. So the thermal equilibrium density operator, like we usually have in NMR, is certainly in the null space of the relaxation super operator. Now there might be additional ones if you have some form of symmetry, but in general, that's the only one.
Okay, I think like we already like gone beyond a lot of like long time, and if you have like further questions, like you can ask Malcolm, and then like so thank you very much, Malcolm, for your very nice presentation. And Bob, you would like to say something, Bob? Unmute yourself, Bob.
So again, thanks to both of our speakers today, Asnatis, for a very nice talk on high field DNP and polarization, and Malcolm for his ever insightful look into the recherche aspects of magnetic resonance. We really do appreciate all the insights you've given us. And next week, Kong, who do we have on the agenda? We've talked about several, and I'm not sure who is.
Sure. I think like the first speaker we have, I don't know like how to pronounce his name. I think like I asked you about this. If you are English speaker, you say like Quentin, but if you speak some French, I think it's Quentin from Sami Janan's lab. And then like the second speaker we have Tatiana. So
Paulinova from University of Delaware, right?
Exactly.
So we're going to have a dissolution DNP experiment and probably a protein DNP experiment discussed, or solid state NMR experiment next week. So quite a different set of topics than what we heard today, but nevertheless, it's going to be really quite an interesting couple of presentations. So we hope everybody will join us again next week, and we really look forward to seeing everyone again. And again, thanks to Asnatis and to Malcolm for really two very inspiring talks. Okay, bye.
Bye, thank you, bye, bye.